what we're going to do here is start off by looking at some different probability rules. So when calculating probabilities, looking for the probability of a certain event occurring. So with this example, we're going to have 10 jelly beans. There's going to be 1 blue jelly bean, 2 purple jelly beans, 3 green, and 4 red. So we have this total sample size. So remember our notation for sample size is n. So we have these 10 jelly beans. And what we're going to do is talk about if we just drew one of the jelly beans out of there, look for the probability of these different colors. So let's start off with just the probability of a blue jelly bean. So if we're looking for the probability of drawing a blue jelly bean, it's that there is one possibility out of all 10 jelly beans. So we have this 0.1. And remember, like I said, we should always change it to a sentence. So we could say like 10% chance of drawing a blue jelly bean. And that when we create this fraction and get this decimal out, we can always think of it as a percent chance. We could look at the probability of purple, which there's 2 purple jelly beans out of all 10, so we create our fraction 2 out of 10. So with that, there's a 20% chance. Probability of green, so a 0.3. And then the probability of red, which there are 4 red jelly beans out of all 10, so a 40% chance there. And then what you can notice is if we add these together, what we're going to end up with is a total of 1. And we get out 1, that's our sample space. It's the fact that we looked at the probabilities of every possible event. So to be within these values, there's a 100% chance, or a value of 1 coming through. So let's talk about if we look for probability of not some event. Say the probability of not purple. So there's going to be a few ways to think about this, and we'll change it into our actual rule for if we're looking for the probability of not some event. So for not purple, it's that there are 2 purple jelly beans. So if we're thinking of just making our fraction, so we want to exclude those 2 purple jelly beans, which leaves us with 8 possibilities. So the idea is that there's 8 possibilities out of all 10. So there's this 0.8. So 80% chance of not choosing a purple jelly bean. Another way we want to think about this is like how I covered up those 2 purple jelly beans, the idea being that we just want to exclude that single event, which it's going to be more helpful to think about it this way for if we, say, had thousands of jelly beans. I wouldn't want to start counting up all of the others. Instead, what we want to think about is, what if we start with 100%, or a value of 1? So this means everything. We take absolutely everything, and the only thing we want to exclude are these 2 out of 10 jelly beans, which is essentially this probability of purple. So if we take 1 minus 0.2, that's going to give us that same value of 0.8 there. But this formula here, this idea of taking 1, or this idea of 100%, taking our whole sample space and just excluding what we don't want, it's going to be a better calculation. So this right here is the complement rule. It says if you want the probability of not some event, take 1 minus the probability of that event. Something I want to introduce here is our actual complement notation. Instead of writing not, what we would often do, instead of writing not purple, you write the event. So we'd write purple, and then it's like it has this, it looks like an exponent of C almost. It has this notation of C. The C is for complement, just means the other stuff. So if we want the probability of not purple, that's the notation that we would use with the C in the upper right-hand corner over purple. So our complement rule says if we want the probability of not some event, and I'm just going to use event A, so if I use that complement notation, A with this kind of exponent C would be probability of not A, you take 1 minus the probability of A. And that's our complement rule. Let's say we look at probability of 2 events. Let's say I'm drawing one jelly bean, but what's the probability that the jelly bean that I draw is green or blue? So, green or blue jelly beans. If I think about, I want to exclude the red jelly beans, I want to exclude with 4 possibilities. So it's like 4 possibilities out of all 10. So there's this 0.4 coming through if we calculate it directly. In terms of our rule, again, if it's not easy to visualize like this, what we're really doing is adding together. We take all of our blue jelly beans plus all of our green jelly beans. So how we could have written this is taking the probability of green plus the probability of blue. So probability of green was 0.3 plus probability of blue was a 0.1, and that would give you the same answer out in the end. And this is our addition rule. And what brings through the addition rule, the key wording is or. Seeing one value or the other. So for us, when we think about or, it can be either. It doesn't have to be both. If we were looking for both, then we'd have the word and in between there. So we want to be careful with the word or versus and. So our addition rule says if we're looking for the probability of some event or the other, so probability of A, what we do is we take the probability of A and add on the probability of B. And that's our addition rule. Now, something that has to come through with this addition rule is that this only works if A and B are disjoint. And disjoint means that they can't occur at the same time. The idea being here, these events are disjoint because pick one jelly bean and have it be green and blue at the same time. So we can't have both of the events occurring at the same time. It's either going to be green or it's going to be blue. It's not going to be some swirl of the 2 colors. So these are the main rules that we want to cover. And let's see, with our complements, probability of not some event, you take 1 minus the probability of that event. Disjoint, they have no common outcomes. They can't happen at the same time. And another word used for disjoint is mutually exclusive. So if A and B are disjoint, if we're looking at OR events, then you just add them together. But let's talk about what happens when we have non-disjoint events, when they can occur at the same time, meaning they can hold more than one characteristic. So for our example, we have students, 24 students in a class, 82% like chocolate, 59% like espresso, 53% like both chocolate and espresso. And this wording right here, the fact that we have a percentage that like both, is key that it's non-disjoint. We can't have that overlap when events are disjoint with each other. So we want to find what's the probability that a randomly chosen student likes chocolate or espresso. So using this rule, let's actually look at a Venn diagram. So a Venn diagram is a nice way to separate these percentages. So when you draw a Venn diagram, start with a sample space. So the space has everything. It has all of the possibilities. Liking chocolate, not liking chocolate, liking espresso, not liking espresso, and liking both. What we do is, if we're focusing on chocolate and espresso, we're going to have these two events. So we create a circle for one event. Let's have this be liking chocolate. And then our other event is the act of liking espresso. And we need this overlap here with the circles because of this overlap of liking both. If they're disjoint events, when we make our Venn diagram, the circles would be separate from each other. There wouldn't be any overlap. We'd have our green jelly beans, our blue jelly beans, but no overlap between the two. But with chocolate and espresso, we do have that overlap. Now what we can do is kind of fill in the blanks using these percentages. So 53% like chocolate and espresso. So 53% of the class is in the middle there. Then what we want to do is use this 82% that like chocolate. However, we won't just write 82% right here because this 53% is part of it. So we want to think about is this whole circle is 82%, but we already have that 53% covered. So we have 82%, take out that 53%, so we have this 29%. The idea being, if you land in this part of the circle, this means you just like chocolate, but you don't like espresso. If you're in here, you like both. And then we want to do the same thing for liking espresso, in that 59% like espresso, but we want to take out that 53%, so there's just this 6% that like espresso, but don't like chocolate. Then our last calculation is who's out here. Who's out in this space where they don't like chocolate and they also don't like espresso? Well, the idea is, if we're calculating this number for this spot, this whole thing, our sample space, is 100%. That's our value of 1. And what we want to take out are these values here. So if we start with 1, take that 29%, take out that 53%, take out that 6%. So if we subtract all of those, then we're left with this 12% out there in that space. So when we have percentages like this, a Venn diagram can be a nice setup for if they're asking a lot of questions about probabilities of certain events occurring. And with a Venn diagram, you see how those percentages distribute. So what we're interested in is the probability of liking chocolate or espresso for these non-disjoint events. To our rule for just adding the probabilities together, so you would take the probability of liking chocolate plus the probability of liking espresso, and let's see why that doesn't work. This is the way that we don't want to do it. So we'd be taking that 82% that like chocolate plus that 59% that like espresso. If we do that, what we end up with is something that's too big. We end up with a 1.41, which is translating to 141% of the class likes chocolate or espresso, and that can't happen. So this doesn't work. But let's talk about why it doesn't work, because our addition rule is going to be pretty similar to this. So let's try it again, taking probability of chocolate, and we start by adding the two. So if we think about what's happening within our Venn diagram, we take the probability of liking chocolate, which is this whole circle right here. So it's covering everything. So we take that whole 82% there. And then we add on the probability of liking espresso, which is the idea of adding together all of this. And where things went wrong is our overlap. What we can see is we've counted this twice, and we only want to count it once. So by just adding the values together, because there's the overlap of them being non-disjoint, we counted too much. So when we do this, what we always have to do is subtract off the probability of both. For us, it's the probability of liking chocolate and espresso. The idea being that we take that 82%, add on that 59%, but then, because we counted this 53% 2 times, subtract it out of there. And this, if we take that 1.41 that we had, and then take out that 0.53, we get out 0.88. And that's our correct value for this liking chocolate or espresso. So you could say 88% chance a student likes chocolate or espresso. And this is our addition rule for when we have non-disjoint events. So that's what's down here. If you're looking for the probability of A or B, you add the 2 events, but you have to subtract the intersection of the 2. And really, you can always use this as your rule. It's just if the 2 events are disjoint, this is a 0 right here, because there is no overlap. Like I drew up here, if you had your Venn diagram, there's 0% in between those, so you don't have to subtract anything away.